Cool. There's no homework due. There's another homework too. I sent in the morning. Basically just go through like the voices we talk about. Um, we would go through this likely on Wednesday about soul separation. But basically this is just to explore what a commercial state of the art, hopefully state of the art, commercialized source separation model is like. So you will do, music source separation. Voices is pretty cool because you can actually choose different kinds of, instrumentation that you want to separate. You can even separate like each drum, each drum in the drum kit. So you can do sort of like so many different ways of music source separation. We will also, look into cinematic sound separation. Basically, go from the mixture into three tracks. One is dialogue, one is music, one is the effects. So here's a bunch of, public domain or public domain. They are interestingly in public domain because they usually fail to renew their copyright. But anyway, the goal is to, separate them into three tracks. Speakers on.
Hola. Don't tell me you didn't know it.
We can actually use this model to separate these tracks into the sound effects, the dialogue, and the music. So this is a very interesting case because this is a 1963 movie, but somehow it's in public domain because UMG at that time, is it by UMG or but basically they forgot to put the copyright notice when they released this movie. So this movie is like immediately into public domain. That's a very interesting case. Because otherwise we won't have anything in public domain, like late in 1963. So the rule for public domain is 75 years in United States. And for music it will be extended to be 95 years. So if you count like 2025 and minus 75 years, it will be 1950, or minus 95 years, it will be 1930. So if you check, all the public domain movies, they are usually before them. So this is like one of the interesting case. And for the other case, some of them are like they didn't renew their copyright. So they end up in public domain. So this is like likely the famous one recently get into public domain. So usually Walt Disney company is the one of the few companies that always, trying to lobby for, extension for copyright. But anyway, Mickey Mouse is now finally in public domain. Not the current Mickey Mouse, but the Steamboat Willie. Yeah. So anyway, this doesn't have any dialogue, so likely not a good target for doing this, dialogue, soundtrack, and effects separation. But anyway, pick one of these you like. These are all in public domain, so you are fine to use those. I could share you with an example, what it look like. Dialogue, soundtrack, and effects. So this is the movie that we just looked at, this one. So if we, for now, it's mostly just soundtrack. But if we get the effects only, it's not sync. But anyway, you get the idea. So you will get the effects and also the dialogue.
Oh, can't you do something constructive like start an avalanche or something? But we will see.
But you can also see that there's soundtrack in the background. And there's dialogue in the front.
What?
Anyway, this is a very interesting case because you can imagine there's other ways to do this. Many applications. Anyway, there's basically homework two. Just look at voices and try the music sound separation, try the cinematic sound separation, and pretty much that's it. So you don't need to train anything. That's what I mean. No code. Just playing with that. Cool. So the instruction is on. I sent an email, so that should be good. Questions? Good. Cool. I guess again, just a quick recap on what we go through last week. So we basically just dive deeper into the deep learning part of it. The goal is not to become a deep learning course, but sort of give you an understanding, or if you've taken, deep learning course, then just, recap what's the core, idea of deep learning is. So again, like how you train the neural network, obviously talk about, the neural network defines a set of functions and you want to define the objective, what is good for a function. That's it being usually defined by, the loss function. And then you want to find the optimal parameters, which leads to the best function. So this is like the three step and the three components of training a neural network for deep learning. So as we talk about, neural networks are parameterized functions. So you are optimizing the parameters, the weights and bias, rather than, the input, because you cannot change the input and output values. You want to see how best you can do to learn that mapping between X and Y. And so your goal is to find the best, function out of this huge set of functions. And the good and bad are determined by, the loss function. So we talk about a bunch of different functions, but, those are not that intuitive. Usually I just, do this, visualize it as a raindrop to see, how these loss behave differently. But generally, it's just measuring their difference. So you can do absolute difference or, the square loss. And if you want to do multi-class classification, this is something we will explore in one of the PA later in class, 2 or 3 weeks later. But basically what you want to do is to try to, get something that's, like a probability like output that sums to 1. So that's our essential goal. So that's why we use this softmax. So we talk about, what the softmax do. Basically, it just, do exponential and then you do normalization. And so once you do the normalization, everything will sort of become probability like ish. So, if you look at the output, it will be, 098, 002, 000. So everything sums to 1, but, there will be relative magnitude to the input. So that's sort of the idea of softmax. And then we talk about, how we going to, maximize. So everything here is about, how you define the loss function, how you define what's good, what's bad, but how do you find the best solution for it? So, in deep learning, we usually use this gradient descent. We talk about, essentially it's just these two lines of code. But more intuitively, somehow this should be in dark background. But anyway, you have a raindrop, and basically you want to find the steepest slope so that you go down toward the lowest point. And you can definitely see how it might end up in the local minima rather than the global minima. So you might stuck in some place. We will talk about how we can fix that later when we actually want to train something. But for now, this at least give you to a better point rather than your initial point. And we talk about backpropagation, but for now, just think about it like a very efficient way of computing the gradients. It's just an algorithm that's much better in parallelizing. Cool. So we will just continue that to finish the last chunk of deep learning fundamentals. So the last chunk is basically about this training validation testing, and usually it's very, very confusing. And oftentimes, when people started working on machine learning, this is one of the biggest pitfalls that people didn't really get it, and there's could be a lot of like generalization issue that can be cause lots of troubles. So I guess the key idea of understanding what this training validation task setup is going on is to think about what's in distribution and what's out of distribution. So oftentimes when you are trying to model a question like a task with deep learning, you always need to think about what's something in your distribution, what's out of your distribution. So think about if you want to do an animal classification, this could be your training set where you have all the standard image of animals. So in this case, if you train on these standard very typical cliche image of animals, does it actually work on some of these more non-standard you know images of animals? So does it generalize like a bear waving hands or different kinds of images? Um, so in this case, the training and test they might be similar, but they could be it could be different. So now you could imagine now if we want to include all different diverse perspectives or different angle of the image could be like or any poses, then you might just include everything in your training data set. Then now it could become another issue, like you could have blurry images or people low resolution, black and white. You can have when you want to test an image classification animal classification models, if you want to test it in real life, then potentially you will have camera out of focus. In this case, how do you handle these? So this now become in distribution, out of distribution. When you train on these, when you test on these blurry images, does it still work? So you always have to think about what's in distribution, what's out of distribution. So finally, even you take care of any of these, you can do data augmentation, just try to, make some of the images blurry so that your data set is much more diverse. But think about what are some of the other case. It could be just visual art. It could be, oil planting. It could be anything else. So oftentimes there's just no way you could model the whole distribution. So, you oftentimes need to think about what's in distribution, what's out of distribution. And that's essentially what you are solving in deep learning. So I guess the key is, make the training distribution as close to the target distribution as possible. So that's the essential rule of thumb when you want to train deep learning models. So, we need to define our target distribution. So you can try to, collect a diverse data set covering different parts of the target distribution. You can also apply data augmentation to fill the gaps in the distribution. So I guess this is a question for you. What do we really want? You know, when you think about training and testing, and do we want good performance on the training samples, or do we want good performance on scene samples in the target distribution, or we want good performance on out of distribution samples? Any ideas?
Can you explain like the difference between like I guess like in the distribution and out of the distribution again?
In distribution is basically the distribution that you care about. So think about the case here. Think about the case here. You care about real animal classification. Do you care about these? You could care about these, but you can, also choose not to care about these. So you always have to sort of like scope it. So in distribution in this case is like the scope that you are interested in. So, what do we really want? The second? Cool. Why not the first one?
Well, on the training examples, you could, I guess, sort of, if you reach, I mean, you could technically, you'd ideally want to have good performance on the training examples as well, but you could sort of overfit if you keep
Yeah.
training examples, and the model loses the ability to generalize.
Yeah. So, I guess a simpler answer to that is that, well, we already have their answers, to be honest. It's like, we already know their answers. So, you get good performance. That's sort of like, well, you should do it. I mean, if it's a machine learning model, you should do it. But more interesting is like, can we get good performance on scene samples in the target distribution? Because, this is essentially what we care about, in our distribution that we care about. Can we sort of like generalize out of the training examples that we have? And finally, out of distribution samples, this is hopefully we can do it, but it's always not guaranteed. And this is one of the case that oftentimes people confuse about. So, think about OpenAI, think about like ChatGPT. Oftentimes people are claiming a lot of things in zero shot performance on the third one. Is that, well, no, good performance out of distribution samples. But in the end, people usually find that, well, that's actually in the distribution that the model is trained on. So this is one of the interesting examples where, to define in distribution or out of distribution, it sort of depends on, your training data, but also what you care about on your task. But out of distribution, generalizability is not always guaranteed, but hopefully we can do something better than just in distribution training. There's also some way you can try to generalize out of distribution, especially when you introduce some of the prior knowledge to help your model, to guide your model. Yeah, so, the goal here is basically how to achieve good performance on scene samples in the target distribution, because technically we don't really care a lot on training samples. It's like we got to nail it, but we don't want to ruin the essential goal of getting good performance on scene samples in the target distribution. Yeah, so basically we are going to talk about overfitting and underfitting. So, this is like an examples where you have a bunch of samples, these blue dots, likely you might see some of these. So, the function, the red function, is it red? Orange, reddish function, orange likely, would have, it's the original function that generate these samples. And, the model, the blue one is that when you have like a degree 4 polynomial to fit it. So underfitting would be something when we see, this model is definitely not expressive enough to capture your model, your data. So this case, we just use a degree 1, linear function to fit this data. It doesn't really work. As you can see that this blue line are so far away from all these samples. But you can also imagine we can get a degree 15, 15 degree polynomials, and it becomes something like this. And this is definitely not something what we want, because it's just like crazily complicated and it doesn't really fit our intuition about what this underlying function would be. Technically, there's no way you can see whether this is correct unless you can get more samples from the function. And that's what we will talk about, the validation set. But another case in 2D, underfitting would be in this case where you just draw a line, doesn't really work. Overfitting would be this case, you just nail it. But what if you get another samples? There's very high chance that it will not fall into this, very complicated boulders. So a good fit will be something in between where, it roughly capture the boulders, but it's not overly complicated. So that's what we talk about, overfitting and underfitting. So now the idea how we achieve this, how can we find a good fit that's not, too inexpressive or not too expressive. So the idea is basically, can we sort of like divide our data set into two? One is training, one is test. So our goal is that, the target distribution is like the whole data set that we have. That's, all we get. There's assuming there's no easy way we can get additional data. We've covered all the data that we have. Then we sort of like mark these as training, mark those as tests. And our goal is to see, can we train the machine learning model on these training samples and we get good performance on those unseen samples in the same distribution, because that's what we care about, the good performance on unseen samples in the target distribution. So one important concept is that test set is just an estimation of the test distribution, because there's no way you can actually get the test distribution. You never know what essentially your test distribution is. And oftentimes you create this pseudo test distribution to mimic that behavior. So we create a test set because we want to estimate the performance when the model is applied to an interested distribution. But this doesn't help a lot when we want to see whether what the model is good or bad. So usually we will also divide this training set into two. So one is training, one is in the middle, is the validation set. So this is where things get a little bit complicated. So the idea is that usually we will train a bunch of different neural network on this training data set. We will optimize it. We will just use, gradient descent or sort of stuff to get a bunch of different versions of it. You could think about, you try different learning rate, you try different models, CNN versus INN, whatever. You train a bunch of different models and you want to optimize it toward its, best version. Now you want to select one of these using the validation set performance to see which one is the best. And then finally, you just pick the best one as the one that you will finally test it on the test set to see what's the generalizability. A little bit abstract. But basically, when you train these kind of models, as you will see in later in the PA3, this is like the training versus validation losses. Ideally, this is what you will get. Usually that's not the case, unless you're lucky enough. But anyway, this is the ideal training and validation loss. Usually at the beginning, training loss will go down, validation loss will go down. And at some point, they will reach somewhere where, training loss will keep going down and the validation loss will go up. And this is when overfitting happens. So what happened here in this dynamic is that, originally, the model is sort of like this, like very, linear to inexpressive mode of fitting. So, the model just tried to fit it with a very bad, function. And over time, once it reached this point, is that, well, now we get a good enough, fit where it sort of like generalized to the validation set, but it doesn't, overfit on the training set. And, after that point, if you keep training this model, try getting a better fit on the training set. It will get better performance on the training set because in this case, if you compare these two, this definitely do better on the training set because they capture all the green into one side and blue to other side. But think about the validation loss. This might not generalize to your validation set or your test set. So this is basically like an ideal case of training for a deep learning model where you go from underfit to perfectly fit and to overfit. So, the idea is basically we just want to pick the model with the lowest validation loss because that's what we care about. We care about, good performance on scene samples in the target distribution. Cool. There's a bunch of these. I guess we could skip it when we have PA3. We can look into this. But some of the key concept is that never train or select your model on test samples, even though people keep saying so. But sometimes even in some of the big AI conferences, you will see people submit papers where they train or select the models on test samples, usually not intentionally. Usually just they didn't realize part of their algorithm is doing this. And also don't over select your models on the validation set. Cool. I guess the rest we could just leave it until we have the PA where we want to train something, then you will get the sense why these matters. But there are some ways you can overcome overfitting. We'll get to these later, but an easy way is that where we just stop here. Or there's something called dropout. We could get into this later. And regularization. Cool. So, the rest of this is basically talking about, this training, training, validation, and test pipeline. Basically, you have you have a data set, you split it into 3 sets. Usually the ratio is 8:1:1 or 6:2:2 or 7, 1.5, 1.5, whatever. But basically you train your models into different versions. You train it. And now in the validation set, you just select one of those that has the good performance. And usually this is ideally what your training loss will look like and validation loss. So at some point, you will get this best performance in the middle where you have the lowest validation loss. That's where you would like to pick your model. Cool. So we will get into the details later on when we have the PA. Then you will realize how complicated it could be. Cool. And today we will talk about source separation. We can listen to it. I guess you listen to it at some point, so we can get drum separate. These are like output from voices, so you can see that nowadays it's already commercialized. It's very good.
Do you remember the days when you said nothing gets in your way?
So it's nothing like this like 10 years ago. If you look at some of the early source separation model, usually there's a lot of leakage into other tracks. But nowadays with, large data set and, good deep learning models, now they're working better. I think my laptop is dying. Hopefully it won't die. Cool. So today we would talk about source separation. Any questions on the deep learning part? Oh, good. I guess mostly just concepts. And, once we reach PA3, maybe there will be more, implementation details. Cool. Cool. So today we will talk about source separation, and this will be homework 2, but also the next PA. Oh, so yeah, PA3. And then, PA4, we will actually do a training. It will be light, but, at least you will get to train something. PA3 will be PA3 and homework 2 will both be source separation. So one would be, homework will you just look at Moises, as I just talked about. But the PA would be, dive into, calling some packages to do it. Still very light on programming, mostly just calling these packages to get a sense how these packages work. Source separation. Cool. So what is source separation? Likely you've know what it is. But basically, you know, a mixture of so many different instruments. We want to break it into different parts. Yeah, I think I don't need to show it again and again. We've seen it. But more interestingly, you know, there's also other kinds of cell separation. You know, this could be a drum set. Where's my set? Oops, I stopped. You know, can we? It won't stop. Can we turn it into like each single drum? In this case. And turns out, you know, now we actually have these models to do this. So let me open up Moses. I actually have one example of those. This one. So, you know, when you upload a track, you can actually select what kind of, you know, separation model that you want to use. So, you know, in the previous case, when you do that, like typical pop song, you could do vocals, guitar, bass, and the whole drum set as one track. And you have piano, wind, strings, and the cinematic case, you can do the street track separation. But in this case, you can even do further, where you go into drum and you know, have the drum kit separate into 6 tracks. And you can also click this to see that you can actually even divide vocals into lead vocals and background vocals. For guitar, you can also turn it into acoustic guitar versus electric guitar, or, you know, lead and the rhythm. So there's a bunch of, you know, details here. But in this case, we are looking into the drum, which is pretty cool. This is everything. We just get the kick drum and the snares and the hi-hat. So the tom-tom is gone. And the cymbals. Yeah. Anyway, you can actually still even like, you know, remix it. But basically, you know, nowadays we have very good models to do all these kind of separation. And, you know, you can define it in different ways that, you know, the outputs could be different sources. But basically, source separation is just solving this question about, you know, you have a mixture and you want to define what would be the tracks, and you want to separate them into those tracks. And it's actually, you know, quite popular nowadays. Almost in every single DAW, you can find some, you know, features on these. You know, in Logic Pro, it's called stem splitter. It used to be not kind of AI, but now, you know, much more AI based. And usually the way how Apple do things is that they don't really let you know what's going on under the hood. They would just, you know, yeah, just do it. And, you know, in FL Studio, there's also this extract stems from samples. I think when you right click the track, you can actually select this, and you will see that you can actually do different tracks. So, you know, many names, stem separation, stem splitter, music, the mixing. This has slightly different meaning, but basically the same idea. Stem extraction, you just want to extract one of the stem. So, you know, source separation divided into different tracks, and then you grab one of the stem. It could be the same thing, but, you know, it could be different. But basically, they are doing similar stuff. And also one of the misconception of source separation is that, you know, source separation does not remove effects. So that's one of the common myth of source separation. It won't remove effects. So, you know, think about how you do music production is that you record a bunch of, you know, tracks, usually dry in studio like this, you know, very quiet. There's no, you know, reverb and, you know, any effects. And then you will apply something on top of it, you know, You apply effects. In the case of electrical guitar, it's a little bit trickier. But usually the case, think about, vocal, it will be dry, and then you apply, reverb or different things. And then you get the wet signals. And usually the wet signals, you will just add them up to get the mixture, do some mixing, there's some panning. But anyway, source separation will only output the wet signals rather than the dry signals. So to go from wet signals to dry signals, that's another task called sound effect removal. And that's all the way till the end of this course. We will talk a little bit about it. It's not solved yet, and I don't think it will be solved quickly because it's very tricky to define what's dry and wet. Anyway, this is like called effect removal. So these are two different tasks. Source separation only cares about going from mixture to the wet signals. So source separation is important in many cases. Usually that's one of the first thing people do. And for a lot of MIR texts, but in this case, physical application, there's a lot of things, remixing, sampling, you just want to grab one track, or we want to redo one of the track. Music practicing and education, think about, recently we're doing some research on a cappella singing vocal coach. So in that case, you have a cappella recording for, SATB, but what if you want to practice? Can you sort of like make it into a karaoke, remove the part, think about if you're an alto, you remove the alto and can you practice along? So it will be sort of like a karaoke thing. But, for music education, can we sort of like grab your, alto singing and then try to analyze whether you are doing correctly, using pitch detection, beat detection, beat tracking. All sort of thing could be, source separation could be the first thing that you want to do. Karaoke accompany generation, again, the same idea. There's also a lot of like MIR tests, music information retrieval tests. Usually source separation is the first step if you want to do a lot of different things. Music transcription, you can separate the tracks and then you do the transcription on each single instrument is usually much better than just apply it directly. You will have like music instrument, vocal detection, singer identification, lyric recognition, lyric to music alignment. So all of these, you sort of need to do, vocal music track separation to enable that. Cool. So these are some of the things just to get you an understanding why source separation is so important, because it has so many applications, both on the creation, music production side, but also on the music information retrieval side. Cool. So for the rest, we will just talk about how does it work, and this will be part of the next PA. I've already released it, but I haven't sent emails yet. Cool. Cool. So mathematically, it's very simple. This is the input mixture will be X, and you have a bunch of source. And to be honest, this is basically what we have. X equal S1 plus S2 plus S3 plus S4 plus S5. That's it. So this is a mathematical formulation, but you can imagine like how tricky this is, because there are infinite ways to do this. Think about X equal 1, S1, S2 could be 0, 1, or 1, 0, minus 1, 2. There are so many different ways to get the same mixture by fine-tuning the sources. So there's a lot more than this equation, but this is, like the mathematical formulation of it, because we know a lot about, what a vocal sounds like, what a piano, what a guitar, what a bass, what drums sounds like. And those prior knowledge will influence how we actually decompose them into these different tracks. Oftentimes we will shorthand as this, but this is just a mention over SI. So that's it. So one thing to keep in mind is that source separation is sort of like one of the questions that's, never gonna be solved. It's an eopose problem. So eopose has even though it has the name of eopose have actually a strict definition, where basically meaning that there are more than one solution to this equation. So in fact, there are, infinite possibilities. But the goal is that, not the goal, I mean, but the intuition or the underlying assumption is that we do know what's more likely than not another. So, in the last homework, we look at this and everybody got it correctly. So, look at these spectrogram. You can sort of like tell from just looking at it, because there are some properties in these spectrograms that you can tell what those are. So, for the trumpet, you will have these, horizontal lines. Those are the harmonics. And for vacuum cleaner, it's basically just noise. So it's like a full, like a noisy spectrum. There is no, harmonics. There is even no, temporal structure. So it's basically just the sounds. So pretty much it's like noise. And for drums, you will sort of have a mixture, because drums, when you, do the hi-hat or the cymbals, you will have like vertical impulse where it sounds like these things, but just like one shot. And, for the drums, when you hit the tongues and the snare drum, you will have horizontal things like harmonic. So this is what you see usually. So the vertical ones are the cymbal, the hi-hat and cymbals, and the horizontal one will be the drums. So, this sort of give you the sense why this could be possible, because, each different instrument has their own characteristic. Okay. And that's what we will use to sort of like do this sort of separation. So that's sort of like motivate what we will talk about the first one. This is also part of the PA3. I always forgot which PA it is. PA3. So this would be the first thing we look into. So time frequency masking. So basically the idea is that, we can look at the spectrogram and we can see that, well, these spectrogram, these horizontal stripes are belongs to trumpet, and these things belongs to drums. Vacuum cleaner likely too hard. But anyway, the idea is that, looking at the spectrograms, there is some way you can actually divide them into two different signals, where one is more horizontal, one is more vertical. So think about it in this case, a bass and drums. And hopefully this is what we want to get in the end of this part. This is what we call harmonic percussive separation. It's a non-deep learning traditional approach. So this will be the horizontal part of this spectrum. That's not what it should sound like. Wait a minute. Let me try again. And this would be the vertical part of that. So hopefully it's not too bad. So, this is like a non-different deep learning models. Basically just look at, what's vertical, what's horizontal. That's it. We will look into how it works, but you can sort of like get a little bit about, this is more harmonic, like, this is more horizontal. It will get all the stripes, the horizontal stripes, and this one will get all the vertical things. Let's listen. So you see those, fundamental frequency. And this one is the percussive one. Yeah, anyway, these are the, impulse. So basically that's what we want to do in the next few slides. What we essentially want to do is not just, directly guess where these are, but rather we want to get a mask. So look at these two things. So these two add to one. But basically, when there's a white part, is that where you want to keep these parts. When there's like black, you want to basically assign 0 weights to those. So what we want to see is that, well, this thing, say this time frequency beam, like a very small time frequency beam at this particular time, at this particular frequency range, do you want to keep it into this track or that track? that's the, the classification things that we want to do. So this is essentially, time frequency masking, or, look at this. This is more like a harmonic, horizontal things. So we want to keep it in the harmonic track. And for this thing, it's more like the percussive things, because this is sort of like, vertical line. So you want to keep it in the percussive string. So basically, you just want to do classification on each time frequency being. So that's essentially what we meant by, time frequency masking. So you will have a spectrogram and you want to do source separation. You want to get, two masks, and you will just apply this mask on top of the original, spectrogram. So in this case, you will get all the horizontal things out. Forget about these, vertical thing, because these vertical thing, they actually, times these, regions that without any magnitude. So, even though there are some vertical thing, that basically times 0. So it doesn't have any effects. So look at all the other part is actually captured in the horizontal thing. But for the lower part, it actually grabbed these, vertical stripes where they have, real values. And once you apply that, you get all the vertical things. So now the question would be, how can we get these two masks so that you can, apply it and then get those, spectrogram, the separated spectrograms out. And, this is just on the spectrogram. So, spectrogram is not the end. We still need to get the waveform, because like you cannot listen to spectrograms. So usually, you will have an audio, you do STFT as we talk about, you get the spectrograms. And, once you have the output spectrogram, you can do ISTFT, inverse short-time Fourier transform, to get the original sound out. So that's basically time frequency masking. We will talk about how we get a mask, but this is the overall, idea of doing classification on each time frequency being. Questions on this? Oh, good. Cool. This is just a misplaced. That's fine. Anyway, homework 2, source separation. The first part will be music source separation. Cool. So we will talk about this. This hopefully we will get this covered for the 20 minutes we have. So basically what we want to do is percussive versus harmonic components. So this is one of the earlier approach that's not deep learning, but would sort of give you the sense why, separation is something doable. So here, basically, these are 6 different things. This is actually what we will do in the final programming assignment, where you want to train note classification models. So look at these spectrograms. You will train a convolutional neural network to predict what the instrument is. So this is the data set that we will basically work on. But in this case, we are not doing that. We could just look at these, different sounds. And you will see that, for these 3, these are percussions. So you will see that they are more vertical. In the sense, it's more like a noise. For guitar, keyboard, and flute, you will see they are like horizontal harmonic stripes. So that's basically the idea of, this percussive versus harmonic components. Percussive sounds tend to look vertical in a spectrogram, and harmonic sounds tend to look horizontal in a spectrogram. So this harmonic percussive separation is like a 2010 paper. So it's actually not that far away. 15 years ago, people are still struggling to figure out a way to do source separation. And that's what we try. And, usually people mark the start of deep learning in 2012. So after 2012, 2015, people started to look into, deep learning. But back then, people are looking into, pure signal processing way to do it. So the idea here in harmonic percussive separation is to apply a median filter over the time axis to make the percussive patterns less prominent. So that's what we mean. So, this is the input, and you can apply a horizontal mean filter. So what we meant by mean filter is that, this is like width equal 5. So you grab this length, this is width equal 5. So you grab width equal 5 here, and then you do a median filter. So in this case, because mostly, purple and black. So when you do the median filter, you basically find the median of that parse. So everything beyond here will be gone. But in this case, the lower part, it will still stay there because, this case, there are like 3 purple bean and 2 black beans. So it will still keep the purple one. But now if you increase this width, in this case, if you increase into width equals 31, then in this case, there's just like mostly, black, 0 values and some, non-zero values. So when you get the median, it will be 0 values. So that will get rid of sort of like all the impulse vertical part of it. But you will keep those, horizontal things because they stay. And when you keep the median filter, they will stay there. So that's basically the idea of, getting a harmonic part. Now for the percussive cup, the same idea, you apply a median filter. What's going on here? Oh, so basically you apply the same thing, but we couldn't really see it. So this is basically, we just zoom in into the 2000 hertz. So these two are the same, but now we just grab this part and then extend it. So this is what you will see. And now these are the filter lengths. So now again, you grab a small chunk of it and you apply this, width of 5 and you do median filtering. This is what you get. And now if you increase that filter into something larger, this is what you get. So basically, now it's a little bit different from the percussive case, but basically now applying a median filter over the frequency axis, again, make the harmonic patterns less prominent, because basically these things get, blurry. So now the next thing, actually, if you look at the percussive part, because everything is, vertical. So when you apply the median filter, everything will still stay the same. But now the harmonic parts will become blurry. So now the core idea is basically you take the output of this and you take the output of this and you compare them to get the masks. So that's essentially what we are going in this harmonic percussive separation. You have a spectrogram, something look like this. You do horizontal median filter, so you get a spectrogram where all the vertical part are gone. You do vertical median filter where all the vertical part will be enhanced, but the horizontal stripes will be blurry. Now you basically just do, when this harmonic part is larger than the percussive part, then you get these, masks. These are things that have more horizontal components than vertical. And the rest will be, when SH is smaller than SV, where you have more vertical components than horizontal components. One thing that's a little bit confusing again on mask is that you see all these horizontal stripes, but these horizontal stripes are actually will times. These stripes are where you have 0 values here. So it doesn't matter whether they are, 1 or 0, because it times 0 anyway. So, this effectively is only the vertical part. Anyway, once you do that, you can do the masking again, apply this onto the mask, you get all the horizontal thing, apply this to the mask, you get mostly the vertical part. Question on this? This is like a very good old, cool, pure signal processing way to do harmonic percussive separation, even though, the output we just heard here about, it's not great, but to sort of give you the sense that, well, each single track has their own features. In this case, we just look at harmonic percussive, but, think about, in modern era, we have multiple instrument, bass, then it will be mostly, lower end, low frequency, mostly monophonic likely. Think about, drum, then it will have its specific features, vocal likely kind of different from other instruments. So that's essentially, we are leveraging these prior knowledge so that to do the separation better. Oh, good. Anyway, we will look into this in the PA. Where you get to call Liberosa. It's actually implemented in Liberosa, so you don't really necessarily need to do a lot of things, just calling it to see what the outputs will be like. But again, the input will be audio. So you have to do SDFD, and then you have to do the inverse short-wave Fourier transform. Cool. We can look into some results. Likely you will get to see this in your PA. But basically, if this is the inputs, the mask, if you look at the mask, it will be gone in the harmonic component. It will show up in the percussive component. If you look at the horizontal lines, it will be captured by the harmonic components, but not in the percussive components. And as I just said, you will see these horizontal stripes in the percussive components, but those are parts that's, zero values. So that doesn't count. Cool. So this is essentially what we have in the PA. Where's my cursor? This is a much, oh, that's it. This is a much harder case than the one that we showed previously. So this is the harmony component. So the drums are mostly gone. You can still hear one bad output here. This is the percussive component. So it's not too bad. It's not too bad. So you mostly still get the percussive part to the percussive components. Mostly the harmonics will be in the harmonic components. This is another example. This is what we get from the harmonic. Oops. So in this case, it's much harder because there is like reverb. So some of these things extend, especially when they're like drums or like extended cymbals, then it will look like harmonics. So you in this case, it's better if you fine tune the filter size. But if you use the default, it's probably the percussive part is really good, but you sort of like get rid of all those extensions, like the reverb. So it's very impulsive. Anyway, in PA3, we will look into this. So basically, you will use the Barossa to do this. Well, let me see where PA3 is. Whoa. Well, super laggy. Cool. So this is like PA3. Again, Google Colab should be good enough. It's not too computationally costly. So the first part, you will need to import the browser. The mux is the other thing we will talk about, the deep learning one. But the first part will be just this HPSS, harmonic percussive source separation. So you will load the example song, you do SDFD, then you just do this HPSS. So this is pretty much that's it. These three lines just do the harmonic percussive source separation, and everything else is just showing the results. There's a bunch of parameters that you can adjust in HPSS. You can go to their documentation to see, you know, how you can change the filter size. So if you look at this kernel size, you know, this is basically kernel harmonic, kernel percussive. So, you know, by default, it's like 31 on the horizontal side and the vertical side. So you can play with it to see how you can do it better. But at the same time, here are, you know, just converted it back. And usually when we convert the audio back, you do this ISTFD basically. That's essentially what you can get. This is the harmonic component. The drums are gone. The percussive one. The drums are kept, but somehow some of the bass still here. So definitely you need to, you know, fine tune a little bit about the kernel size. Cool. Anyway, that's the first part of HPSS. The second part we will go into it soon. But that will be doing with this DeMux. It's one of the deep learning based music source separation model. It's open source. So, you know, unlike Moises, it's like, oh yeah, it's great. It's like doing commercial grade separation results, but you know, you have to pay for it. We got it for free, but you know, after you graduate, then you have to pay for it. But the Max is one of the open source model. And the result sounds like this. You know, this is the input, same song. So you can do drum versus non-drum. So this is the non-drum track. So I would say pretty good. Not as good as the commercial one, but it's good enough. Another example. This is the drum tracks from the DeMux output. This is the bass. We didn't hear everything else, and this is the vocals.
Little time with my man, sweet darling.
That's it. Yeah, sometimes it's like audio effects. But anyway, you know, DeMux is also very easy to use. Basically, this is a line that you want to do. DeMux that separate that main, and that's it. And you will get the output saved in a folder. So that's basically you will explore just to get a sense how these, you know, open source model work. Shouldn't be too tricky. It's just basically calling these models that's already online somewhere. Cool. So that will be PA3 first part and second part. The second part will be deep learning approach. But this part I can go through it a little bit. But most of it we will need to understand a little bit about, you know, convolutional neural network to get a sense. That's what we will talk about on Wednesday. But you know, the basic idea is that now we don't do all these, you know, like media filtering, signal processing stuff. We basically just want to map directly from this mixture spectrogram all the way to the predicted sources using a neural network. So now you can think about it like it's just doing classification on each single frequency, time frequency bin. For each of these time frequency bin, which, you know, source it should goes to. And, you know, once you have the outputs, of course, in the beginning, it will be nothing like this. It will be a mess, everything like very bad. But hopefully at the end, it will be closer to the ground truths that you have. So basically, you will just measure the difference between these two by some loss function. It could be, you know, MSE or whatever absolute difference. But basically, measure the difference and you try to apply the things that we talk about, you know, gradient descent, backpropagation, all sort of things, and so that you train the model to optimize the parameters so that, you know, these things become better and better. It match the ground truths better and better. So this is like the spectrogram-based models where, you know, for each time frequency bin, you try to guess what the output spectrogram would be. But you can also just directly apply it on the waveform. This is more like a recent progress. In the past, people don't think that you can apply it on waveform directly, but nowadays, given how powerful these machine learning models are, you can actually just directly predict the waveform. So again, you have to measure the difference, and then you train the model. But can you guess what would be the key difference between these two? What would be some issue here when you measure the difference on the loss function? We sort of mentioned it last time. What would be the question when you work on waveform and you want to measure the difference? When you inverse the waveform, it sounds exactly the same, right? So you take a waveform like 1, 0, 1, 0, you turn it upside down, 0, 1, 0, 1. It's basically the same, frequency domain. It's just like softly like offset. So that's all the problem of, all these waveform-based models. So in this case, how do you measure the difference? You just take them minus, or, do some absolute difference, MSE square errors. So simple. And then you train the model. But in waveform case, usually it's very much harder. You cannot just do it by just taking them and, minus do, difference. Because essentially in waveform domain, so many different, variation of the same waveform, they actually sounds not exactly the same, but pretty much the same. So you have to handle that. So usually actually, when people want to measure this difference, there's actually a way you can turn FFT into a differentiable operation. That's one thing very cool about machine learning nowadays, why we can do a lot of like waveform thing, is that when we compute the loss function, we can actually grab this waveform A and waveform B. We do Fourier transform, fast Fourier transform, and then we get the spectrogram, and then we compute the difference between those two spectrogram. And everything of these, because Fourier transform is a not linear. Fourier transform is a differentiable operation. So you can actually backpropagate the gradient back through the whole FFT thing. So I just want to say, when you work with waveform, it's much harder than people expect because, technically, if you take two waveform and then just minus them and think about, well, we just do MSE, mean square error, it doesn't work because usually it doesn't work because, when you take them and minus them, you don't necessarily want to match the waveform directly. You want to match its frequency components rather than its specific waveform in the end. Cool. Anyway, this is what the mux look like. We will get into what those are. These are basically convolutional neural network. We haven't go through it. We will talk about it on Wednesday. But anyway, that's what the mux is. Once we talk about CNNs, convolutional neural networks, we will come back to talk about the mux. Cool. Cool. So that's basically what we talk about on Wednesday. And there will be the second part of PA3. Cool. Yeah, there's much more, but cool. You on Wednesday. And yeah, homework 2 will be due next Monday, right? No, next Wednesday after the break. And PA3 will be even further away. Cool. Yeah.